This week, we're going to focus on the very useful and maybe not very widely used getLayer function. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, I want to talk about a function that's in metpy.calc called getLayer. It's a very useful function and one that I don't know if a lot of people are aware of. getLayer takes data that has a pressure and optionally a height coordinate, so think a sounding or some model output, and will subset that. So maybe you only want to know a certain layer's mean wind. Well, this gives you an easy way to get that data out, and it can even interpolate the bounds. So we're going to take a look at how that works with some real data, and I'm going to show you not all of the permutations that you can use this with, but some of the more common ones. So over here in our notebook, of course, we're going to start out with a big block of imports. metpy.calc is mpcalc, because that's where our calculation lives. From datetime, I'm going to import the datetime object. From metpy.units, I'm going to import the units registry, as well as pandas data frame to unit arrays. From siphon.simplewebservice.wyoming, I'm going to import the Wyoming upper air object. Matplotlib, and our matplotlib inline magic. And this is units. All right, so first we need to get some data. I'm going to get some sounding data. For the last couple weeks when we were looking at calculating thermodynamic parameters and gridding them, we were using the Iowa State archive. Now we're going to use the Wyoming upper air archive just to mix it up a little bit here. For the date, I'm going to create an instance of date time, 2021, 6 month, 27th day, 0 hour. And for my station, we're going to do Dallas-Fort Worth. Going to create an instance of this Wyoming upper air object. Use the request data method. And we're going to give it our date and station. Of course, Shift-Tab brings up the quick help if you forget the parameters that this method takes. And now we've got a warning, but that's okay. We can ignore that. And let's look at the head of our data frame. We've got pressure, height, temperature, dew point, direction, speed, UV wind, station, station number, time, lat-lon, elevation, and precipitable water. Now, lat-lon, elevation, and precipitable water, as well as time, station number, and station, all are the same. It's just that the data structure we've chosen here, which is the data frame, doesn't let us have scalar values for those. So we just duplicate it throughout the whole column, as these aren't huge data sets anyway. So it's not using that much memory. So now let's get out of a data frame and into some unit arrays. So I'm going to call this data. Pandas data frame to unit arrays. We pass our data frame. Now if you remember, our data frame has a units attribute that we inject. That's actually what's causing that warning that we saw, where we have a dictionary of the field name and the unit. So what pandas data frame to unit arrays does is looks at that units attribute, or you can specify this manually if you don't have a units attribute on your data frame, and returns to us a dictionary where the key is the variable name and the value is a united array. Notice we have units down here. All right, so let's go ahead and work with getLayer. mpcalc dot get layer. And we remind ourselves of the signature here. The first thing that we need to provide is pressure. From our data, that's pressure. What's next? Star args. This means as many variables as I want, because everything else is a keyword-only argument. So anything I pass now, we're going to get the subset back. So for example, I could pass speed for wind speed and direction for wind direction. I could continue adding on here temperature, dew point, whatever else I wanted. But for now, I'm going to stick with those three. It's going to return me as many things as I've put here in args along with a pressure. So I'm going to get a pressure subset, a speed subset, a direction subset, and it's going to be equal to the return of get layer here. So we can run with no further input. And what do we get? We've got pressures from 986 to 886. What did our pressure data look like? It started at 986 hectopascals. Okay, so let's look at the docstring a little bit. The height, we're not providing any heights right now. We're not providing any bottom, which means it's going to start at the highest pressure value or the bottom of the data. And the depth has defaulted to 100 hectopascal depth with interpolation on. So we've gone 100 hectopascals, 986 to 886, and we interpolated that 886 because, as you notice in the data, there is no 886. So that is the default behavior. And if we wanted to, we could go ahead and plot that. Maybe we'll just plot, and we'll plot it with some plus symbols there. Yeah. So there we see our interpolated data point and the data for our 100 hectopascal layer, and we've already got the units marked since these are unit arrays. So not much work for quite a bit of gain. Okay, let's do this again. And I'm going to copy and paste, and then we'll modify just so we can go over several permutations in a few minutes here. All right, so we've got our standard. Now let's try specifying a bottom. I can specify a bottom of 900 hectopascals. Notice in my data, I don't have a 900 value, and I don't have an 800 value. But if we look at what we get returned, it's 900 to 800. So we have interpolated. And we didn't change the depth, so that is still the default of 100 hectopascals. Now, basically everything in here you can specify in pressure or in height. If you give the function height data, it will use that. If you don't, it assumes a standard atmosphere, and we have the citation for that in the documentation. Okay, so let's turn interpolation off. Interpolate is false. And if we look at P subset, now we went from 910 to 819. So it is between 900 and 800, but with no interpolation this time. All right, let's look at a couple more variations here. I'm going to leave the bottom where it is, but now I'm going to change the depth. So I'll specify a depth of 300 hectopascals. All right, so that works. We went from 900 to 600. I could also specify a depth in terms of height. So I'll leave the bottom where it is, depth, and let's make depth 200 or 2000 rather meters. So now we've got what it believes is 2,000 meters of a standard atmosphere worth of data. So we're going up to around 700 HPA. And again, we're interpolating by default unless we turn it off. So we can mix and match our units here. And then finally, we can also specify heights. So for here, I'm going to set the bottom to be at 1,000 meters. I'm going to specify the depth to be 5,000 meters. And the height data is our data height series, or in this case, united array. Now we're actually using the height data, and we're getting a 4 kilometer thick layer from 1,000 to 5,000 kilometers. So getLayer is a really handy function that doesn't do anything overly complicated, but it's very versatile. It lets you do complicated queries on your data quickly without having to think about converting from a standard atmosphere or to a standard atmosphere, or worrying about particular starting and stopping points or interpolating. It takes care of all of that for you. I hope that you found this useful, and I'll see you on next week's MetPy Monday.